This is a P3 replay for the Orbital Interactions lesson. The problem you're looking at here covers this interesting reaction between a dioxarane, which is characterized by an OO bond in a three-membered ring, and an alkene. And as you can see, the final result is epoxidation of the alkene, that is, addition of an oxygen atom to the two carbons of the double bond, and the production of a ketone, which is derived from the dioxarane originally. So recognizing these details of the reaction is actually going to turn out to be very useful for this problem, because we can see what bonds are made and broken, and from that we can reason backwards to the likely molecular orbitals that are involved here, which the frontier orbital interaction involved in this reaction is really the crux of what this problem is about. So a transition state for this process is shown here, and remember the transition state is just a point on the reaction coordinate where the energy is a maximum and bonds are partially formed and partially broken. So what we can see here is that the bond between the two oxygens in the dioxarane is breaking here, and two new bonds are forming from the two carbons of the alkene to that oxygen atom. In addition, we're getting the formation of a double bond between oxygen and carbon in the dioxarane. And really, if you focus your attention in on this area, what we can see is that the key frontier orbital interaction here is between some nucleophilic orbital associated with the double bond and some empty orbital associated with the oxygen-oxygen bond. We know this because the oxygen-oxygen bond is breaking essentially. Right? Essentially, those electrons are what are contributing to the new oxygen-oxygen double bond. And so it's likely that an empty orbital associated with the OO bond is going to be involved as the acceptor in this interaction. And in fact, the orbital involved is the sigma star. The OO sigma bond is breaking, so the sigma star is receiving density from the donating or nucleophilic orbital. Now the nucleophilic orbital, really, it makes sense that it must be the pi orbital associated with the double bond. There's really no alternative. The sigma bond of that carbon-carbon double bond is left behind. The double bond is not, and actually gets involved in the formation of one of the new sigma bonds. So it's the pi molecular orbital that serves as the donor, the sigma star that serves as the acceptor here. The second set of blanks ask us about the kind of overlap and about the number of nodes in the LUMO of dioxarane. So let's start with the overlap. What you can see in the transition state is that the axis of the p orbital, or the pi molecular orbital from the double bond, is parallel to the axis of the sigma star orbital, which is pointing right in that pi orbital's face. They're parallel to one another and they're coaxial, which means that this must be sigma type overlap. Remember, sigma type overlap involves head-on overlap of the two components, and these two are actually pointing right at each other. Don't be fooled by the fact that this is a pi molecular orbital. The overlap between these two molecular orbitals is nonetheless sigma type. So we can immediately fill in that blank. To determine the number of nodes in the LUMO of dioxarane, we need to actually look at the LUMO. There's no way really to reliably determine that just from the transition state picture or the reaction. So opening up the associated link here, what we need to do is just identify which orbital is the LUMO, first of all, and second of all, inspect it for however many nodes it has. So hopefully your eye went straight to this molecular orbital table and you identified orbital 16 as the LUMO here. We can then easily pull up orbital 16, rotate it in the JMOL, and what we see here is that there is a node here on oxygen, there is another node on the other oxygen, and there is one directly between the two oxygens as well. Notice that the node that's on carbon is actually in the same plane as the node that's between the oxygen atoms, and so this is counted as a single nodal plane. So there are three nodal planes here 3 nodes and submit, and we see that we got the problem correct.